In the previous section, we talked about interference and how the interference patterns that you see with light was historically one of the important pieces of evidence that people pointed to for why they felt that light was a wave. The second big piece of evidence is diffraction. Diffraction is a behavior that waves exhibit that allow them to bend around obstacles in their path. We can refer to the obstacle as either a hole, so you've got a barrier like the one over here on the right where there's some hole in it, or a pole is the word that we'll often use simply because it rhymes, where there's just something relatively small sitting out there that the wave goes by. And what we see when we see diffraction is you see the waves bending. So either they'll bend around some small obstacle, so they'll bend around the pole, or they'll spread out from the hole. One example of this that you've probably seen is that if you think about, say, some pole sticking out of the water on a lake. So let's say you've got some dock, it's got some pole that's helping hold up the dock. Waves come in towards the shore, and of course, as they reach the pole, they don't just go past the pole in a way such that the water behind the pole is never disturbed. What they do is they bend around the pole to close that back in. And so this is the evidence that you would be looking for to see whether or not light diffracts and acts like a wave. So if there were no diffraction, you'd have some wave starting out here on the left that would come into this hole, and the part of the wave that lines up with the hole would be the only piece of the wave that you would see go through. Again, there would be no adjustment. There wouldn't be any bending. Well, so the question we want to ask is, what happens when we do this with light? And sure enough, when we look at light and how it behaves around obstacles, we see diffraction. Here you see a diffraction pattern. There's this large bright spot that's spread out. So this has come through some slit that's really small. So the fact that this is spread out at all is in and of itself showing you that the light is bending as it comes through that hole and you're seeing diffraction. But more interesting than that is that we have places where the light disappears. We have minima within this diffraction pattern before you have some secondary bright spot that again shows the light bending into places where it couldn't have got through if it just came through the hole before you get another minima. And so in terms of the light intensity, you see a pattern that looks like this, right? Here's that central bright spot. And again, the slit is just this thin little sliver that the light came through. So the fact that it's spreading out over this initial bright spot, this central bright spot, is in and of itself showing us the light bending as it comes through the hole. But then we also see on either side of that central bright spot a series of minima and then a smaller peak, and a minima and a smaller still peak, and a minima and a smaller still peak. So you see the light fall off, but more importantly, we see these series of minima within the diffraction pattern. So the question is, why did it take until the 1800s for us to really see this? Well, and the answer is because you have to have holes and poles. So your obstacles, whether they're a slit, some sort of aperture, or you have something sitting out in front, has to be on the order of the same size as the wavelength of the wave. And as we know, the wavelengths for light is sitting somewhere between 400 and 700 nanometers. So you needed really small slits and really narrow obstacles to see diffraction occur. And so that's why it wasn't until sort of later than what you would have anticipated that we recognized where we were seeing this and what this behavior was. So if we come back and think about our interference pattern, with two-source interference, we said that we had a source, a second source, they were separated by a distance d, and so what's interfering when we saw the pattern on the screen made some sense. We said light coming from one source is interfering with light coming from the other. It gives us this triangle. That triangle lets us figure out what the path difference that the light coming from one of those sources travels farther than the other, and then we can use this right triangle to relate the path difference, the angle theta, and the slit separation d. Well, how do we then explain what's going on with diffraction? Because with diffraction we just have a single slit. So A here is the slit width. So D is our slit separation in our interference problem. A is the slit width. How wide is your slit? So the first question becomes, well, what is it that's interfering to cause this pattern? And what we're going to do is we're going to use the Huygens principle that says that if you have a wave front, and so the wave as it comes through this slit is a wave front, we can think of it as being made up as a series of point sources. And so I can break up my wavefront using the Huygens principle into a whole bunch of individual sources. And so now what I can see is that I can start matching these up. So if I think about this source that's sitting just inside the top of the slip, if I come down to just past the halfway point, now I've got a source that if I can get these two to match up and interfere with each other, now I see two sources that are interfering to cause my diffraction pattern. And then these next two will interfere with each other, and these next two. So Huygens principle letting us break up this wavefront into a series of individual point sources lets us see how we're going to end up making this work to get our diffraction pattern. So we're going to say that light coming through the slit up towards the top is going to interact with light coming through the slit just past the halfway point, so that I can get all of the light sources up here to interact with all the light sources down here in exactly the right way to get these things to cancel out. And so again, what that does is it gives me a right triangle. Here's my right triangle. The hypotenuse of this right triangle is half the slit width. So this is A over 2. The angle theta here is the same as what the angle theta was in the interference problem. It's the angle that you've moved away from the central point in your pattern when you look on the screen. And this angle theta to get you to that point on the pattern is the same as this angle theta in the right triangle that I care about. And opposite that angle is the path difference. So how much longer is the light coming from this point source down here traveling than the light coming from this point source up here? That's given by my delta lambda. So I can use sine theta again and say that, oh, well, sine theta is opposite side over hypotenuse, so that's got to be the path difference over half the slit width, and I can solve this and get that the path difference is equal to A over 2 times sine theta. Well, once I know what that path difference is going to be in terms of the geometry of what's going on at the slit, now I can think about where the minima occur. So again, if I know that the path difference is equal to A over 2, so half the slit width times the sine of that angle that tells me how far away from the central point in my pattern I am, well, I also know that minima occur when that path difference is some integer value plus 1/2 wavelength. So half a wavelength, 1.5 wavelengths, 2.5 wavelengths, and I can plug that in, and what that lets me solve for is an equation that says I can figure out where I'm at in my pattern. So where I am in the diffraction pattern, how far of an angle have I come away from the center line. That's going to be equal to the nth minimum times lambda over A, where again A is the slit width. And here, just like in our interference, we're using n because we're talking about a minima, and that n starts at the number 1. And so what I have is an equation that lets me solve for where I am in the pattern, and it depends on the wavelength of the light that I'm using, the width of the slit, and the number minima I'm interested in seeing in the pattern. Now, of course, just like with our interference problem, there's another relationship that's helpful, and that says, hey, if you've got your slit sitting over here, the point we're looking at in the interference pattern that's an angle theta away from the center line, I can now relate to some distance that that point sits away from the center line on my screen. So I have a second equation that lets me relate how far on the screen I am away from the center line. So y is a distance along my screen, and L, of course, is the distance from my slit to the screen. So where is it that the light's coming through the slit? How far does that have to travel to get to the screen? So this gives me a second way to calculate out what's going on with theta that is now thinking about how that angle away from the center line relates to some distance away from the center line on the screen.